hit start on this contraption. Go ahead.
There you go. I'm Austin, and I did my project on simple linear regression. So linear regression, a little background, it's basically approximating the response variable using a linear combination of predictors. And then a linear combination is just anything expressed as a coefficient multiplied by a variable. And it could be like a sequence of them added together. So when do we use simple linear regression? When we have a quantitative response and we have a quantitative predictor too. We can actually use it in other cases where it's not a quantitative predictor. You just have to make sure you make a dummy variable when you are making your model. And so, like you can see over here, there's a quantitative response, quantitative predictor. And so that would be a case where simple linear regression would be used. What assumptions have to be met to use simple linear regression? There's 4 of them. So first, a linear relationship has to exist. That's pretty obvious. If there's no linear, it's linear regression. You have to have a linear relationship there to use it. You need a normal distribution of the y. That's shown off right here. So essentially, the distribution of the y has to be bell-shaped. And if it's not, you have to do some sort of transformation to the y, whether it be log, square, something like that, to take care of the skewness. You need independent observations. This is only really an issue when you're collecting data on subjects over time, and like one y value is connected to the next one. Like your blood pressure in week 1 is connected to your blood pressure in week 3 because you're the same person. And then you need constant variance, and an example of non-constant variance and constant variance is shown in the corner here. And on the left, you have non-constant variance. You can see how it expands as x expands. And then on the right, you have much better, where variance is a lot more constant. So for ordinary least squared regressions, that's the most common type of regression. What you want to do is you want to minimize the sum squared residual, and that's this term right here. The whole front part, that's your e, or expected value of y given x. That's your fitted value for the response, and that's given by fitted not, which is an intercept term that can be interpreted as the fitted value when your predictor variable is equal to 0, and then beta 1 times x, that's your slope. Your beta 1 is your slope, and that can be interpreted as the amount you'd expect y to increase by a 1 unit increase in x. And then to get to the actual y, you have to add an error term that's always going to exist. But with ordinary least squares regression, we want to minimize the sum of squared residuals. So essentially, minimize the residuals and get the best fit we possibly can. Here's just a picture of a simple linear regression model. You can see the x-axis, the y-axis. There's a very clear linear relationship between the two, and then you can see the values for beta naught and beta 1. 80 being the beta naught value, that would be what we would predict for x equals 0, and then for 1 unit increase of x, we expect y to increase by 2 units, as you can see there. So to test for significant results, you run a t-test on the beta 1 to see if x helps explain y, and your null hypothesis for this would be beta 1 equal to 0, and your alternative beta 1 not equal to 0, and then your t-test, you take, so that that lowercase b1 is your estimate for beta 1, and then you subtract the value if the null is true, so that would be 0, and then you divide by your sample error for b1, and then after that you run a two-tailed p-value, or p-value. You get a two-tailed p-value on that t ratio by looking at normal distribution with the right number of degrees freedom, and then that will give you a probability that you have a beta 1 as extreme as what you observed. So R squared, R squared is another way to tell how well your model is fit to your data. It tells us the percentage variation explained by your regression model, and then that's calculated by 1 minus the sum squared of residuals divided by the total sum squared. So that's error, and that's just if you just fit the mean for everything for that second one. And it's the correlation squared, so if you take the square root, that's the correlation between x and y. And here's a simple example. I made a jump. The y's are 1, 2, 3, 4, and 5, and then it's just 1 through 6 is the x's. And you can see it follows a somewhat normal distribution, so it's that assumption is met. And then you can see, looking at the scatter plot, that it follows a pretty linear trend, and there really isn't any issue with residuals or variation expanding. So then I fit a line for that, and the linear model that it spit out was 0.4 plus 0.743 times x plus the error term, and that's so our beta naught is 0.4. That's what we'd expect for x equaling 0, and then for a 1 unit increase in x, we'd expect 0.743 increase in y. Our t ratio for that for x for the beta 1 is equal to 10.61, and then the p-value, so the probability that we have a t ratio as extreme as what we saw is 0.004, so that tells us we have significant results, and that x helps predict y, or it helps explain y. And that's my presentation.